Have you ever wondered if we're truly alone in the universe? Or if there are other worlds out there, perhaps similar to our own? These questions have intrigued humanity for centuries, and thanks to modern astronomy, we're starting to find some answers. Exoplanets, or extrasolar planets, are planets that orbit stars outside our solar system. Unlike the 8 planets we're familiar with, exoplanets are distant and often very different from the worlds we know. The discovery of the first exoplanet in 1992 was a groundbreaking moment, opening the door to a field of study that has since captivated scientists and the public alike. Discovering exoplanets is no small feat, especially considering how distant and faint these worlds are compared to their host stars. Over the years, astronomers have developed several ingenious methods to detect these elusive planets, each offering unique insights into their properties. The most successful and widely used technique is the transit method. This method involves monitoring a star's brightness over time. When an exoplanet passes or transits in front of its star, it causes a slight but detectable dip in the star's brightness. This dimming occurs because the planet blocks a small fraction of the starlight as it crosses the star's face. By carefully analyzing these light curves, scientists can not only confirm the presence of a planet, but also determine its size and orbit. The Kepler Space Telescope, launched by NASA, has been instrumental in using this method to discover thousands of exoplanets, including many that are Earth-sized and potentially habitable. Another crucial method for detecting exoplanets is the radial velocity method, also known as the Doppler method. This technique relies on detecting tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. As the planet orbits, it exerts a gravitational force on its star, causing the star to move slightly in a small orbit of its own. This motion affects the star's light spectrum, causing it to shift towards the blue or red end of the spectrum, depending on the star's movement towards or away from us. By measuring these shifts, astronomers can infer the presence of a planet, estimate its mass, and even gain insights into its orbit. While the transit and radial velocity methods have been the most fruitful, other techniques also play an essential role in the discovery of exoplanets. Direct imaging, although challenging, involves capturing actual images of exoplanets by blocking out the starlight, allowing the planet's faint light to be seen. This method is particularly useful for studying large planets far from their stars. Gravitational microlensing, on the other hand, relies on the gravitational field of a star and its planets, bending and magnifying the light of a more distant background star. If a planet is present around the lensing star, it will cause a detectable blip in the magnified light, revealing the planet's presence. Each of these methods has its strengths and limitations, but together they provide a more complete picture of the diverse and fascinating worlds that populate our galaxy. Now that we've covered how exoplanets are discovered, let's delve into the diverse types of exoplanets that have been found. Just as the methods of detection vary, so do the characteristics of these distant worlds. Exoplanets come in a wide range of sizes, compositions, and orbits, some of which are quite unlike anything in our solar system. One of the most common types of exoplanets discovered are gas giants. These planets are similar to Jupiter and Saturn, with thick atmospheres composed mostly of hydrogen and helium. They are often several times the size of Earth, and many orbit very close to their host stars, leading to extreme temperatures. These hot Jupiters, as they are known, were some of the first exoplanets to be discovered because their large sizes and close orbits make them easier to detect using the radial velocity and transit methods. Super-Earths are another intriguing category of exoplanets. These are rocky planets like Earth, but with a mass up to 10 times greater. Super-Earths can vary widely in their atmospheres and potential for habitability. Some may have thick atmospheres and surface conditions similar to Venus, while others could have conditions more akin to Earth. Their larger size makes them easier to detect than Earth-sized planets, and they have become a primary target in the search for potentially habitable worlds. Beyond gas giants and super-Earths, there are also ice giants, similar to Uranus and Neptune in our solar system. These planets have thick atmospheres, but are rich in water, ammonia, and methane ices, which form deep beneath their atmospheres. There are also water worlds, planets where oceans could cover the entire surface. These oceans might be hundreds of kilometers deep, offering a tantalizing possibility for life beneath their surfaces. Finally, some exoplanets are so unique that they challenge our understanding of what a planet can be. For example, rogue planets are exoplanets that don't orbit any star, drifting freely through space. Others, like carbon planets, may be rich in carbon and could have diamond-studded surfaces. Some exoplanets orbit so close to their stars that their atmospheres are being stripped away by intense radiation, leading to exotic and extreme environments. The diversity of exoplanets discovered so far has expanded our understanding of what is possible in planetary formation and the conditions under which planets can exist. From gas giants to rocky super-Earths, these distant worlds offer a glimpse into the vast complexity of our universe, and they raise new questions about the potential for life beyond our solar system. As we explore the variety of exoplanets, one of the most intriguing aspects is the search for planets that could potentially support life. This brings us to the concept of the habitable zone, sometimes referred to as the Goldilocks zone. The habitable zone is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. Water is essential for life as we know it, so finding exoplanets within this zone is a primary focus in the search for extraterrestrial life. The exact distance of the habitable zone depends on the size and temperature of the star. For example, around a star like our Sun, the habitable zone might be located at a distance where Earth orbits. However, for smaller, cooler stars like red dwarfs, the habitable zone would be much closer to the star. When we talk about the potential for life on exoplanets, scientists look for biosignatures, which are indicators of life that can be detected from afar. These could include specific gases like oxygen, methane, or ozone in a planet's atmosphere, which on Earth are produced by living organisms. The presence of liquid water, a stable climate, and the right chemical elements are all critical factors in determining whether a planet might host life. The search for life on exoplanets is a central goal of missions like the James Webb Space Telescope, which is designed to analyze the atmospheres of distant planets. By studying the light that filters through a planet's atmosphere as it transits its star, scientists can detect the presence of certain molecules and assess the planet's habitability. Several ambitious missions are on the horizon that aim to expand our understanding of exoplanets. The European Space Agency's PLATO mission, scheduled for launch in the late 2020s, is designed to find and characterize Earth-sized exoplanets in the habitable zones of nearby stars. Plato will complement existing missions by focusing on bright stars, which will allow for more detailed studies of their planets. NASA's LUVOIR is another exciting mission in the planning stages. LUVOIR will be a powerful space telescope capable of directly imaging exoplanets, including those that are Earth-like. With its advanced capabilities, LUVOIR could revolutionize our understanding of exoplanet atmospheres and surface conditions, bringing us closer to identifying planets that could potentially support life. In addition to new missions, technological advancements will play a crucial role in the future of exoplanet exploration. Improvements in telescope design, such as larger apertures and more sensitive instruments, will enhance our ability to detect smaller, Earth-sized planets and analyze their atmospheres. Techniques like adaptive optics, which correct for distortions caused by Earth's atmosphere, will allow ground-based telescopes to achieve near-space quality observations. In just a few short decades, the study of exoplanets has transformed our understanding of the universe and our place within it. From the first discovery of a planet orbiting another star to the identification of thousands of diverse worlds, the field of exoplanet research has rapidly evolved, opening our eyes to the vastness and diversity of the cosmos. The quest to find Earth-like planets and potential signs of life continues to inspire and drive technological innovation. As new missions are launched and our detection methods improve, we are poised to make even more remarkable discoveries. Each new exoplanet discovered adds a piece to the puzzle of the universe, helping us to understand how planets form, how they evolve, and whether life might exist beyond our solar system.